Welcome to the video on binary and hexadecimal. In this video we'll be looking at how to write in and convert between binary, hexadecimal, and normal digits, which are also known as decimal numbers. And this is important because both binary and hexadecimal are used extensively in networking. So it's important to understand because in the case of binary, it's how the computer interprets the data. So it's important to be able to think and understand the data in the way the computer does. And also for hexadecimal, because as we'll see, it's an easy shorthand for representing binary. So we'll start by comparing how binary counting works compared to normal counting. So again, our normal numbers are commonly referred to as decimal numbers, and that would be 0 through 9. And in binary, as implied by the bi, there's only two digits, a 0 and a 1. So let's start by illustrating what everybody should be familiar with, which is how we would count in normal numbers. And we'd go 1, 2, 3, all the way down to 8 and 9. And when we get to 9, what we do then is we go 0 here, and then we would add a 1 in the next column, right? So we'd get 10, 11, 12, 13, 14, and so on. And then the same thing would happen when we would get up to 99, right? Both of these would go to 0, and again, we would add a 1 in the next column. So binary works pretty much the same way, but since there's only two possible digits, the columns tend to fill up faster, and we'll see the columns expand rather quickly. So we'd start with 0, and then 1, and then because we've already exhausted the possible numbers, this will then become 0, and we'll put a 1 in the column here. And so let me just write a few more of those. So the next number then would be 1, 1, and then because these columns are both full, we now zero them out and put a 1 in the next column. And so this would continue on indefinitely, or until we've come up against the maximum number of binary digits that we want to use. And binary digits are commonly referred to as bits. Now, as you'll see, once these numbers start to become multiple digits long, obviously they aren't exactly intelligible. Just by looking at it, it might not be obvious what the decimal value of 111 would equal. So let's look at how you would figure out the value of those digits. And so what we do is we start with the ones place, or the first place, or first bit, and it's going to have a value of 1. And then it's a simple rule to remember is that each place is double the value of the bit to the right. So this is going to be times 2 the value, so it will be 2, and then times 2 the value of 2 for the next place to the left, it's the value of 4, and we could keep going, so 8, 16, 32, 64, and 128. And again, as you'll see, each place to the left is double its place to the right. So 2 is twice as much as 1, 4 is twice as much as 2, and so on. And we can scale this as high as we need, but typically 8 bits is what is commonly a common unit in computers, and 8 bits is referred to as a byte. 1 byte. And also it's important to know that the value of this is anywhere between 0 and 255. And we can figure that out by basically adding all the numbers in the value place up, and you'll see we'll get 255. So that's the maximum number that can be represented by 8 binary bits. So let's say, to give a couple examples here, and we'll just we'll use 4-bit numbers to keep it simple. So let's say we have a binary number of 1001, and we need to figure out the value of this number. So if we refer to our chart up here, there's a 1 in the 8's place, a 0 in the 4's place, a 0 in the 2's place, and a 1 in the 1's place. And all we do to figure out the value is for any bit that has a 1, we add them together. So in this case, we would add 8, and we don't add 4, and we don't add 2, but we would add 1. And the value of that then would be 9. And so, again, we add up all the 1 bits, so to speak, based on their values. So to give another example there, if we have a binary digit of 0, 1, 1, 1, so we'll fill in our chart up here, we're not going to count the 8's place, but we are going to count the 4 place, we are going to count the 2 place, and we are going to count the 1 place. And so the value of our number there is going to be 7. Now, we pretty much use the same logic in reverse when trying to figure out if we take an existing number and try to convert it to binary. So let's say that we're trying to figure out how to write the number 7. So if we draw our chart up here again, so 1, 2, 4, 8, what we want to do is, starting with the largest number, basically subtract from this each place that's possible. And so, for example, we can't subtract 8 from 7 without getting a positive number or 0, so we would put a 0 in that bit. Now, because we can subtract 4 from 7 and still have a positive number, we'll put a 1 there, so we'll do 7 minus 4, which gives us 3. And because we can take 2 away from 3, we'll also put a 1 in that column and subtract 2, giving us 1. And because we can take 1 away from 1, which gives us 0, we put a 0 there. And so we've successfully converted our decimal number 7 into binary with 0, 1, 1. So let me do one more example of that. Let's say we want to find the number 10. So drop our chart here again. 1, 2, 4, 8. Now again, because we can take 8 away from 10, we'll put a 1 in the 8's place, giving us 2. So obviously we can't take 4 away from 2 and get a positive number or 0. So that's a 0. But we can take 2 away from 2, which will give us 0. And so then obviously we can't take away 1. So our binary number in this case is 1010. Now, let's take a look at hexadecimal. And what we'll see is that hexadecimal is actually derived as a way to write binary digits in shorthand. And the reason for this is that a hexadecimal digit equals 4 bits and can be written as a single digit. And the digits are anywhere from 0, and so in addition to the normal 0 through 9, they've added A through F. And the way that works is, as you count up, so you get 8 and then 9, and normally, right, we would then go put a 1 in the next column and 0 it out and start over. But in the case of hexadecimal, we actually keep going, and so we'll go 8, 9, A, which has a value of 10, B has a value of 11, C, D, E, and F, which is 12, 13, 14, and 15, respectively. Now, this might seem like kind of a weird way to go about numbers because it sort of complicates the calculating. But again, the reason this was invented was to become shorthand for 4 bits. And so let's take a look at that. We'll drop a byte here, which, as you'll recall, is an 8-bit number. And I'll put our values under here for reference. Now, as you'll recall, when we go to convert this binary string into a normal decimal number, we'll have to add everything together where the bit is set to 1. So let's put a binary digit in here. And if we were to go ahead and convert this, again, we'd add up all the ones. So 128 plus 64 is 192 plus 16 is 208 plus 2 would give us 210. Now, the convenient thing about hexadecimal is instead of having to add up a potentially large string of numbers, we can just break it down into these 4-bit chunks. And so we'll separate this from this, and so these will keep their values, but now we'll redefine these also as 8, 4, 2, and 1. So in this case, if we add them together, we get 13, which, if we consult our chart here, is going to give us a value of D. And of course, this one's pretty easy. It's 2. And so we could represent 210 instead as D2 in hexadecimal. So I'll give one more example of that. And so let's take another string. This time we'll do 1110, and we'll just do a single digit this time, and write our values up here. And so this time the value is going to be 8 plus 4 plus 2, which gives us 14. And so I'll write our chart back up here. A, B, C, D, E, and F. And 10, 11, 12, 13, 14, 15. So in this case, the binary digit is going to be E. And so, again, anytime we have a number go above 9, but still basically between 10 and 15, we're able to represent it using the expanded hexadecimal digits. And similarly, when we're trying to convert from hexadecimal to binary, we just have to remember to take the existing numeric value and convert it to binary. So, for example, if we wanted to convert C back to binary, we would just do the same as we did before. And so we've got 12, so a 1, and a 1, and then 0, 0. And so pretty simple converting back and forth there. Thank you for watching, and we'll see you in the next video.